I appreciate all of your being here. Um, I just want to say, with all of the insanity that's been going on, um, from getting kicked out of the dorms to just how everyone's handling this and the potential of um, the disease actually affecting people close to you. Thank you for being here. It means a lot, not just to me to have students to teach, but it's to that things still go on. So I really, I can't say that aside from when I was in school during 9/11, that I've ever seen something like this, and just the rallying of students behind like still going and doing their thing is pretty remarkable and pretty inspirational. So thank you guys. It makes my job worth it. It makes me proud, damn proud to be a Wolverine myself. So keep at it. And like, yeah, I've been trying to say, make sure if you have any questions for me, please don't hesitate. Just email me. It's totally fine. You can post them in the chat, whatever you want. But like, go blue, man. Go blue. All right. So, before I tear up now on video forever, posted to official recordings, today we're going to be talking about pressure vessels. And, as if there's not enough pressure on everyone, let's talk more about pressure. We're talking about stress and strain. We're applying that wholeheartedly to life right now. But today we're gonna go through pressure vessels. It's a bit of a sort of one-off lecture, and it's going to go through. We'll talk about hoop and radial stress, stresses in open containers, um, and so where we were last Monday. There was no class Wednesday, of course. We had our first Twitch stream and talked about eccentric loading, where we have our object and we apply forces not along the centroidal line, and instead allow for bending to occur due to we can rewrite that force as a centroidal force plus an additional couple moment on the edge. So today we're going to sort of have a little bit of that, but if we have internal pressure inside a beam, or a vessel, how does that change our kinds of analysis? And maybe to start, we have a lot of examples of pressure vessels, and I'm sure you could contribute some in the chat if you'd like. But why don't we just start listing off a couple of these? And I've put over here this pretty wide range of length scales here. You've got all the way down to microns, all the way up to kilometers, and pressure vessels are really at any of these length scales. So down at the sort of micron to millimeter level over here or so, we actually have biological systems. So specifically blood vessels range really hugely, going from arteries up top to capillaries near the bottom of that range. And so, you have different kinds of pressure that are exerted by cells, exerted by things flowing through, blood, but it's one of the wider ranging ones. And on the total other side of the spectrum, from, roughly the order of meters to kilometers and above, this is where we have things like dams, which are open vessels for sure, but oops. But this just goes to illustrate what the difference is on length scales that we can really see. And I'll put a couple more in that are sort of interest in general, which are, for example, pipes. We can range from about millimeters to sort of citywide applications of above meter. So this would be like pipes and tanks. We have pretty common ones like, food, beverage containers, right? So unfortunately, this is a kind of beer, but not real beer. It's just ginger beer. Sorry, you guys thought I was cool. Who am I kidding? No one thought that. So we got from millimeters to maybe I'll say meters for barrels for home brewing. Let's say we have our food containers. And then we also have, let's say, a pretty common one here is airplanes, probably on the order of 10 to 100 meters or so. So we'll say airplanes and submarines. And artillery is another example where you see maybe on the order of millimeters to maybe a meter plus. This will be artillery, guns, cannons, etc. Heck yeah, Moscow mules are fantastic. I don't know if I can officially sponsor that, being that this is actually a lecture, but 11 out of 10 would recommend. So usually when we're talking about pressure vessels, we are referring to not just the internal pressure, but really the difference of the internal and external pressure that are on the system. So this is called the gauge pressure. So gauge pressure, and we can define that specifically. So the gauge pressure is equal, well, let's call it P. And this is equal to the difference between the internal and the external pressure on a system. So what I mean is inside our vessel will have a PI and outside will have a P infinity. Pressure is in, whoops, oh, I don't have double tap on, that's right. So pressure is in pascals, just like stress is. So this is usually what we're talking about, just to sort of simplify the system so we don't always have to deal with the external pressure, from atmospheric or whatever. We're really looking at what's the difference of those two to get a sense of if we're under tensile or expansive pressure here, like vacuum versus applied internal. So in general, we can say that the pressure P can be above zero, but it can also be below. And there are a couple dominant examples of those. So let's say it can be above zero. So this ranges, anything from tanks to airplanes, where you need that additional pressure to avoid avoid that when you go up into the atmosphere, the actual air pressure drops. Or we can similarly have the P is below zero, and this is, for example, for submarines, where you're trying to maintain something like atmospheric pressure, but you have all of this additional hydrostatic that's being applied by the water. So, we can consider both, and we can do so pretty generally. So why don't we look at, if we're to take a free body diagram of one of these guys and make a cut through it. So let's say we have this pressure vessel and it'll have some, I don't know, let's say we have some gas inside, right? So we have in here, we'll say we have some gas. And then we'll just take a cut right through this. All right, we'll take a cut right through here. So we'll put our little scissors. And what we see at this cut for this particular one, which is a little, it's not the best pressure vessel. We have a little bit of asymmetry here, let's say. So let's say we have some area associated with this. So we'll say we have some example AZ. But the interesting thing is we can do our free body diagram two different ways. We can either decide to leave the gas in, or we can take the gas out when we do our FBD analysis. It's sort of like if you want to take one component of your system versus taking multiple components and treat that as one combined object. So for this one, let's say we leave the gas in the system. All right, so I'm gonna keep this. We'll keep the gas inside the system. And what that's going to do is when we go to write our normal forces on our system, we have an additional one that we don't always have. And it's going to be applied right at this surface right here. And what's that going to be? I'll open it up for responses right now. What is this? What's going to be applied in addition to what we would normally see, for example, with our axial and our shear and our moment. At that purple area, we're going to get something else. What is that? So I see gas pressure. Yeah, that's exactly right. So we are going to now, because we split this surface right here, and we've removed the gas that's pushing against that exact plane when we took that cut, right? It's sort of that if we take a segment through any part of our gas, there's going to be the other side of the gas that we've gotten rid of would have been exerting force on that. So we do additionally have this pressure that's going to be right at that plane where we've made that cut, leaving the some of the gas inside the cylinder still. If we didn't have that though, and I'm going to let's see how best I can do this. Maybe I'll remove this for a second. If we took the gas out, all right, I'll put it back in a second, but if we took the gas out, what we'd have instead is additional force acting all along the inside of the container from the gas that we removed. Right? We could either take the gas out and then put the forces or the pressure all over the inside surface of our object, or we can leave the gas in there. Any force it's applying on the inside of the container becomes an internal force, and we only have the one at the surface. The calculations work out exactly the same way, and in fact, your web reading goes and shows both of those different examples. I'm going to continue on with the leaving the gas inside the container just to make our calculations a little bit easier, but we could have done this either way, just for the record. All right, so that considered, now we have a couple more things we need to apply. So we've done the slightly weird one, but we can leave the ordinary analysis that we've done in the past. So if we cut through something that's uh, long and skinny, we're going to get a couple different components here of our force and moment that we would ordinarily have, right? So what am I missing? What do I need to put on my diagram here? What do I still need along my centroidal axis to apply? Yeah, exactly, right? So I need to apply the additional normal force, right? The internal normal force, internal moment that would ordinarily be applied just by the thing being connected, but it's just something we have to draw in here because we have our cut going on. Exactly correct. So we'll put that in. We'll have our little NZ here. I have my coordinate system over here, so Z is along the axis like we normally take. And we'll exactly have an additional, let's say, M around the x-axis, right? Because x is pointing out of plane. So we have an additional mx from bending. Potentially, we have our nz pointing along that axis, and we have p as well as our area. So now, most of what we're going to want to determine is what's the stress going on inside this thing? Is it going to break, right? Do we have to worry about our material failing? And so we have to get our stress. So in general, we want to know the axial stress sigma zz. This is our goal typically for these kinds of problems. And we've been doing this for a bit. We've been trying to find the axial stress sigma zz, right? But we need a couple additional ways of treating we need a new way of treating the pressure in order to get what the axial force nz and moment now are, because we have potentially an additional stress component from there too. So I do want to also mention that we're going to be solving for axial stress here, but in general, a pressurized container is going to try and expand if we put more pressure on it too. So that tells us that the stress is also going to be in another direction as well. We're going to have hoop stress going around the circumference, and we're going to have, if we had a little bit imbalance, we could also create something like shear. So we may have additional um, additional stress components here too. So it won't just be axial today. We're going to look at those other ones as well. So we'll say there are other stress components too. Components too. And so we have to analyze these as well. All right, so we're going to start with a simplifying assumption here. And we're gonna call this a thin cylinder. So if we have our can of soda or juice, we will have this particular geometry in order to simplify some of our assumptions, and I'll go into what that means in a second. So we'll call this a thin walled cylinder. And specifically, that means there's a relative ratio of how big your radius has to be with respect to how big the thickness has to be. And for common engineering applications, we assume the ratio of R over T has to be greater than 10. That's not like an exact hard and fast rule, but it changes the amount of error you would ordinarily have if you were to assume that maybe it was a thin-walled cylinder, but it wasn't actually. So specifically at 10, the prediction for what the hoop stress would be, the prediction for hoop stress, which is going to be sigma theta theta in our new polar coordinate system, is going to be under. It's going to be under predictive by about 4%, which is typically tolerable. We can usually deal with that. But if we go under 10, if we have that ratio not quite be 10, it's going to get worse. So under 10, it's a lot worse. All right, so let's transform into polar. Why don't we, life's lesson, when I say juice, I'm just meaning beer. I'm just trying to not say it during my lecture, that's all. So we have, let's say we take a cut of our object right here, and we're going to look at one little segment that we cut out of it. We're going to have a little representative volume here that we can cut right through the entire thing. And so now what we want to do is describe actually which components are where. So the first thing we want to do is draw this little element and see where our stress components are and what directions they carry with them. So we'll use this little coordinate system down here. And so if we're looking at any stress that's operating in the vertical direction here, it's the same direction our radius is pointing. So this is going to be our sigma RR here, our radial stress. And then we're also going to have additional components going this way, potentially going this way. But it turns out for a thin-walled cylinder, if you apply a uniform pressure inside it, you don't actually generate any shear. You just get this change in stress that's purely normal. So to just double check our directions, our left and right sides are going to be the faces that are changing in theta. So this is our normal stress in the theta direction, meaning that there's, again, a force that's applied in theta with an area that's pointed in the theta direction as well, right? And then finally, our out of plane ones are going to be pointed in the z direction, and we're considering force components in that direction as well. So we have sigma zz going in and out of the page, sort of on this not quite isoclinic, but roughly 3D view here. So I want to define these as, first off, our axial stress. This is our usual, force per area, or at least has been our force per area to date. We're now going to have a pressure component of this as well. And then we have in the theta direction going around in that circle, it's aptly called the hoop stress. And this is the official term for it. And finally, the RR is our radial stress. So in general, I'm using a polar coordinate system for this, but you don't have to. These can be described as sigma XX and sigma YY in a Cartesian frame. You just have to keep track of what direction they're pointing. So if you were to use X and Y, you just make sure that your area and your force are pointed in the direction you want to describe, such as X and Y, right? You just want to make sure that they line up the way you expect them to. So this depends, let's say, on orientation. Depends on orientation. Okay. So now that we have our little diagram here, the first thing we want to do is find, all right, what's our axial stress going to be? We've been doing that sort of the whole time. So let's go about this thin symmetric cylinder and see what we get. All right, so just like before, we have a cut where we assume that the gas is going to stay inside the cylinder, and we're going to have this pressure now being applied to that face of the gas that's going to be trying to compress the cylinder. Because again, we've split the gas. The gas on one side is going to be applying pressure, and the entire object is going to feel it. On the other hand, we could also have a normal force being supplied by just the cut through the actual material itself. So we have to keep track of those two components, and we could do that in our force balance equation right here. So if we then take the sum of the forces in Z is 0, we have two things that have to go into this equation, right? So what are they? What are the two things that have to go into this equation? I'll open it up to the chat. And I'll drink some coffee. Oh, you can hear me drinking. I'm sorry about that. I keep forgetting this. I listened to my lecture and it was like gulp. So my bad. So what am I summing here? Just to normal force and the force, exactly, normal force and the force exerted by the gas pressure, and that is a force that I'm trying to get, right? So I'm going to have to take first off NZ, and that's fine. So we can put our normal force NZ, good, and then we're going to have this additional minus P, but this has to be turned into a force, right? So we have a pressure. The way we can turn a pressure into a force is via an area. So what we need is this area right here. And this is going to be pi r squared, right? But actually, why don't we zoom in a little bit? So before I write pi r squared, so over here in this diagram, I put the r specifically right at the middle. So I'll draw a little, actually, this is fun. So to this point, right in the middle of the volume, is what I'm going to call R. And this distance from top to bottom is what I'm going to call T. So really, the radius we have that this pressure is going to be going from the center of that object to that inside radius is not R, but it's R minus T over 2. So we'll just put that correction in here. So we'll have an R minus T over 2 squared. All right, so this will be important later, and this will actually sort of clarify why we make some of these assumptions that T has to be small. So when we expand this in our Taylor series, or get all the terms in there and then neglect some of them for being small, that's the reason we can do this. So we'll start with that, and we'll then get our expression for NZ, and we'll get finally that NZ is equal to pi times just our R minus T over 2 quantity squared times P. All right, so this gives us our axial, we're pretty good to go. Thank you, appreciate that. This gives us our expression here. And so now, let's say we want to actually get what we need to eventually get to the other component of axial stress, and that's getting what our area is as well. So, all right, is it flickering? Because I can try and, yeah, it might be my connection too. If I have to, I can go to wired, but I might have to change rooms. If it gets really bad, please do flag it in the chat, and I can try and move locations. Okay. Hopefully the recording will be pretty good though. So if it does cut out, there would also be that as a backup. But if it becomes bad, I'll try and fix it. Okay. All right. So let's say we now have the area we need to get because our axial stress equation down here is just the total normal force divided by that area this is going to be exerted over AZ. And AZ is just going to be that ring around the tube, right? So we want to get that total area here, which is going to be pi times the difference in these radii squared. So we have an r plus t over 2 squared minus an r minus t over 2 squared to get that outside minus inner radius and get that area between them. And so if we expand this out, the r squareds cancel and the t over 2 squareds also cancel. We're just left with the middle term, which is going to be a 2r times t, well, r times t over 2 times 2, which gives us just rt. So what we should get from this is that this results in 2 pi r times t. And from here, we can just plug that in. So we can take our normal force NZ equation from over here and plug that in. So we have pi times r minus t over 2, quantity squared times p. Divide that by the expression we just got for the area, 2 pi r t. Again, just from doing this expansion. And we can cancel stuff out. And, you know, here's where we want to use that approximation, because if we have just r minus t over 2 quantity squared times p over 2 rt. Well, if we have that r minus t over 2, if r over t is greater than 10, r minus t over 2 is going to be approximately r. So we can then cross out one of those r's, cross out the bottom one, and get an approximate expression for sigma, which is, so we'll say this is, let's say it's r squared p over 2 rt, cancel out one of these guys, and get our final expression for axial stress here. Sigma ZZ is approximately PR over 2T. All right, I'll box this because this is a pretty important equation here. Or I'll try and box this. So I'll draw a box around it. Hope for the best. There we go. Beautiful. So this is the axial stress in a thin-walled cylinder, but there's a caveat on this, and this is discussed more in the web readings. This is only for if you're not applying more axial force. Only for no additional axial force. If you're applying a whole bunch of other stuff, we can't just solve for NZ, right? We would have additional results on that. So in general, you have to be careful of when to use this approximation. And we'll actually talk more about that on Monday when we do the combined loading case, where we actually do have generally additional forces being applied to the outsides of the cylinders. All right. So good question by Bob the No Builder. Will all pressure vessel questions in this class assume thin wall? I think in general, yes. I think I'm not going to go too far into where radial, it tends to be the radial stress that makes the big difference there. But we can, yeah, in general, use the thin wall approximation. I'll probably say it in a question that it'd be applied at least for like the exam for sure. So, and then why is it r minus t over 2 for the first area? So the reason for that is I'm defining the radius of the cylinder to the midsection of the wall. That's sort of a convenient definition. I could have had it just going from 0 to r, and then r plus t, it would give the same result. We're going to go over how to find the stress. It was yeah, we'll go into that more on Monday. So I will do an example for combined loading where we do apply another axial force. I think there was one in the reading for this week, and I think the web reading specifically. I think there's one for Mondays as well. So I'm happy to go through details. Probably I'll do that more Monday because it's going to be a combined lecture and example session. So we'll cover that in more detail. All right. Thank you for the questions. This is pretty great that I'm getting like real-time feedback. The red note on page 1 being Maggie, I assume you mean this one. So that's the that's specifically for when you can say sigma zz is approximately PR over 2t. If that is not the case, so that's the same actually, and I'll color this in red. This is that same note that we're saying r minus t over 2 squared is approximately r squared. All right, great. So, stream lagging. Okay, hopefully not too bad. All right, so I'll pause for a second just to check in on everyone. Is the stream okay? Are you seeing this all right? Hopefully, can you hear me okay? Is it glitching a lot? Let's find out. Okay, it could be if you're logging in a little bit late. It might be why. All right, cool. So let's move on then. Hopefully my internet connection holds up, and all of your internet connections hold up as well. So in general, we may have other loads, and actually this is where this would be applied, and so this is just sort of a sneak peek. But if we do apply other loads in here, so let's say we have an additional applied load that would be on the other side. Let's say we have an actual force being applied here and another moment being applied here. The way to treat this is just to incorporate that into the stress equation later. So we have our what we'd find for NZ after doing our balance. Similarly over that area AZ, but if we had an additional couple, we would have to put an additional bending axial stress on here as well, and that's fine. You can just proceed as usual. Proceed as usual after this. So this is the way to go about it. Like I said, we're going to cover it more Monday, but that's generally the ticket. Okay, so that's how we treat the axial stress, and now we're going to move to the next stress component, which is the hoop stress. And we hadn't really dealt with these other stress directions, because typically when we have a beam, we don't load it transversely. This is where we have internal pressure that's actually causing transverse loading. So if we want to find the hoop stress, sigma theta theta, it's dependent on not just what the pressure is inside it, but it's similarly dependent on the radius, right? Because that'll change the area. So it's this hoop stress is dependent on radius. And if we're using that thin cylinder approximation, we're going to have this r minus t over 2 is not less than, is approximately equal to the actual value r, which is approximately equal to r plus t over 2. And what we can use this in a similar vein, where if we approximate this, we'll get a similar approximated stress value that will hold for our thin cylinder assumption. But if we wanted to, we could incorporate that additional approximation. So instead of cutting this lengthwise now, or instead of cutting this flat along the side, just chopping right through it, what we want to do this time to get to sigma theta theta is to cut along that direction that points in theta, right? We need both a force component and also an area component that are both in theta, right? So what we can do is we can cut the cylinder lengthwise. And if my drawing of this isn't as good as you need to visualize this, Hibbler actually has quite a good example of this. But what we want to do is cut this, and then I'm just going to rotate. I'm going to rotate this a little bit here. But inside here, we're going to have gas, and I'm going to draw the cut plane in purple here, which is the boundary of where this gas is being cut along. And so we're going to have, just like we did before, these pressure components that are going to operate right along that cut. Pressure due to gas is basically just a normal force. We're not really getting friction near the sides. We can treat it essentially as we did normal forces earlier in the semester. So we have our pressure P just like we did prior. And then we have a little different of an area associated with our cut surface now. So we've cut through here. And so our area is now not quite the entire circle. It's just this thin little strip on top and thin little strip on the bottom. So if we want to write out what our area, and this is no longer AZ, this is A theta, right? Because we have that unit vector pointing in theta. This is going to be what now? What is this A theta going to be for just one of these rectangles now? I'll open that up to the chat. So I see a TDZ, right? Yeah, so we have our thickness and we have our change in position along the length. Exactly. So this is just TDZ. And we have two of these, right? Because we're going to have to balance our force being carried by the top surface and carried by the bottom surface. So we'll have two of those. All right, good. So now we need to get our equilibrium, right? We have to do our equilibrium balance here. And so we have two forces we have to care about. We have our force that's going to be applied over here by this object trying to hold itself together, just as we all are trying to hold ourselves together at this point in time, or at least I am. We are, I can assure you the faculty are going just as crazy as everyone else out there. And so we're going to have two of these, and they're going to point in one direction. All right, so we have, maybe if we want to cut, I guess our coordinate system is sort of split. If we take it from the center, our theta is going to sort of go around. So if we take it from the top and actually just split this area, I'm going to move this P. Let's say we split this area here. Let me draw that a little better. If we split that along this plane, just because if we were to go around theta, one would point one direction, the other would point the other. If we want to get something that's non-trivial, we could just split this on the top. And so we'll get, for that particular balance, right, we'll have a f theta. So let's say we have this f theta, pointing in theta. And we additionally have minus the resultant of this pressure being applied on this surface. And so to get that surface, what do we have here? We have a length of this, which is r minus t over 2. And it also has a width of dz. So it looks like we have f theta minus r minus t over 2 del z times p equals 0. Right, and so we can solve for f theta, which is the radial component of the force at that cut, and get just the result here, which is p times r minus t over 2 del z. Okay, so far so good. We found out what our force has to be, and so if we look for what our stress then is by taking our force along that direction divided by the area pointing in that direction, so f theta divided by a of theta, we'll just have our p times r minus t over 2 del z, And then our area that you guys generated from before, which is T times del Z. And so looks like we can cancel del Z out, which is good. But here's, another example of where we can use that approximation, right? So if R over T is greater than 10, then we can call R minus T over 2 approximately R. And thus, actually, you know what? I'll just write this as the full expression, which is sigma ZZ is approximately PR over T. I'll box this one too. All right, so I'm going to pause for a second, and I want to highlight something, right? So just as I forget what your first name is, M Strike, is it Matt? Why am I not remembering? I'm so sorry. But so, we have Michael, sorry, Mike, yes, of course. I'm still trying to remember last names. I'm sorry. So yeah, Michael, where's the factor of 2 coming from, right? If you wanna, if you wanna, is that sigma theta theta? Well, yeah, sure. A half or two. You're totally right. You're absolutely right. And I'm trying to. Sorry, that should be sigma theta theta. My mistake. You're all totally on top of this. Yes, sigma theta theta. Good call. Thank you. Thank you, Andrew. Thank you, everyone. Keeping me honest out here. I love it. So exactly, where's this factor of 2? It's over here versus not here. So yeah, I agree. There is a difference of what amount of stress is being experienced by this pressurized object in the hoop direction versus the outside directions, right? And that's pretty important. And actually, it's exactly the reason I think at the beginning of the semester I posted, or not posted, but in the lecture slides I had, there was an example of hot dogs from a pressure cooker, and they all burst along the length, which is exactly why that happens, because the force it takes to rupture the material is half as much in the round direction as it is on the end caps. So this actually has serious design implications where we generally have to care more about the hoop stress in terms of failure criterion than we do the force at the end caps, which is why the end caps can sort of have whatever shape they want, but the cylindrical part is pretty susceptible to exploding and can split along that length. So yeah, there is a factor of 2, and it's very important design-wise. Okay, so now we can talk a little bit about this last component. So we've discussed the axial part, and we also have the hoop part that we have to care about. So let's discuss the radial stress now. So the one just pushing on the material outward, and this is going to be sigma RR. And let me draw a better sigma for posterity. That wasn't really a better sigma. Third time's the charm. There we go. So if we look at what our stresses are on the inside surface and the outside surface, I'll actually look at that question by Andrew. Does this equation also only work if there are no extra forces? Yeah, if you were to put an additional force on the outside, you would have to take it into account for sure. So you'd have to do that same sort of force balance, make sure you're taking into account all the extra forces being applied. So that's actually why, for example, we use gauge pressure. Because if we didn't, we would have to take the internal pressure and then subtract off another term from the external pressure, which is another reason the thin-walled assumption has to be there, because that outside area would be slightly longer than the inside area, right? So yeah, you would absolutely in general have to care about that, and that's a pretty good point. All right, so to just continue on with radial, if we have our radial forces here, we pretty much are only going to be restricted by, well, we're only applying forces to the inside surface and potentially the outside surface if we have external pressure. If we're using the gauge pressure, we'll only have the inside one as a resultant. So on that inner surface, the resulting stress just has to balance the pressure of the gas associated with it, which is just minus the pressure being applied, so minus P. And on the outer surface, if we don't have any additional gas pressure being applied, this is just zero. So the average stress going on at point R is just minus P over 2, which, because we have R over T, which is a fairly large factor, it turns out that this isn't super important for us to care about design-wise. And frequently, we can actually neglect the effect of that additional pressure causing radial stress. So I'll write that over here, which is since P R over T is going to be much larger than P over 2 because R over T is greater than 10 for this for the assumptions we've been using, we actually have a pretty common approximation. Is that sigma RR is basically 0. That's usually okay to assume in these kinds of applications. All right. So if we want to, let's say we want to look at a different kind of geometry. Instead, let's look at spherical pressure vessels instead of the cylindrical kind. By doing the same sort of analysis, where we take our force balance in, let's say we have two directions now. Let's say we have a phi direction and we have a theta direction. We can run a similar analysis with a bit more geometry here. And thank you for handling that question, Wani. So we can have a similar kind of balance with a bit more geometry that I'm not going to show here. But using that same sort of symmetry, what you end up getting is that the both expressions actually have to be PR over 2t instead of PR over t. So spherical geometries, and this is actually drawn pretty well in Hitler if you want to take a look for more detail about it. But it's an important design consideration that for things that are more spherical, there's no additional concentration of where that force is going to be applied in one curvature direction versus two curvature directions. So it sort of bears the load a bit more evenly and has a lower failure criteria, which is important. So this is more here for highlighting that they're a little bit different, rather than me deriving the whole thing to bore you all in the next, not really a lot of time. So it's sort of cool that just by doing the same analysis, you can show that you get a better survival rate, so to speak, of your pressurized vessels by making them more curvy than less. All right. So at this point, what I want to do is go through an example. I'll go through one sort of quickly, and then have another two that I'm happy to work through for not just the people here, but also for the record. Though if you have other commitments or classes you have to go to, by all means, do leave and go do those as well. But I do want to work out solutions just so you have access to that. And then I'll have my office hours right after in case anyone wants to chat about ones in particular. So here's an example problem that's like one that could be, on an exam, or more than being on an exam is like a fairly important kind of problem for engineering design. And so let's say we have a cylindrical pressure vessel of some radius. And what we do is, you can't just make one pressure vessel easily. You have to bolt two halves together. So let's say we have 20 bolts. We put it along a flange that's going to be at the midsection. And we want to figure out what the normal stress in each bolt is going to be if we have a certain diameter of them. Is it going to be critical? Are we at risk of breaking this pressure vessel or having explode or whatever? Obviously, we don't want that. So the way we do this is, we start with our drawing, which is over here on the left, and you basically can approach it the same way we've been doing a lot of these problems already, which is you take a cut where the bolts are, you try and figure out what the forces are everywhere, look at the pressure that's being applied inside the vessel, and off you go. So let's say we have let's go and start actually drawing our FBD here. And so what we're going to have is these forces that the bolts are applying. And so if we collapse all of this into one plane in theta, you can make sort of a resultant, and we'll just say we have 10 of these on one side and 10 on the other side, just by sort of taking theta from 0 to 180 and collapsing that down. And then we're also going to have, where's my purple? We're also going to have an additional pressure acting along the surface due to the normal force of the gas on this side, right? So this is where we put in our pressure, which we know to be 1.35 MPa. And off we go. We can now start analyzing this thing. So if we take our equilibrium across our center plane, which is based on our coordinate system, let me zoom out a little bit. We just have a z here. So if we take the sum of the forces in z, we just resolve the pressure and add up the other two forces. And so this gives us just 20 times F, so this plus this, 20 times F minus, now we have our pressure that we have to turn into a force, right? So we need an area there. So minus 1.35 megapascals multiplied by that area, and we know the radius, and that's pretty much all we need. So we have a pi times 0.75 meters squared equals 0, right? And so we can solve for what F has to be by multiplying our numbers out, and I'll even write this. So 1.35 MPa times pi times 0.75 meters squared divided by 20 just gives us a result of 1.19 times 10 to the 5 newtons, or 12 kilonewtons or so, or 120 kilonewtons or so. And so from here we can just get the axial stress on each bolt by taking sigma zz equals that F divided by the area of each respective bolt, right? So if we have an A bolt, we can write our force, 1.19 times 10 to the 5 newtons. We have to divide by the area of the bolt, which is pi times, we have a diameter up here, turn that into a radius if we want, 10 millimeters squared. And we get a final result of circle. No, not circle. 380. It's like comedic relief, I swear. 380 MPa. So it was a pretty casual example, not really super involved. All we had to do was find an axial force. We had balance. We weren't applying any other additional forces exterior to that. We're pretty much good to go, right? So all our assumptions check out. I should have said that the cylindrical pressure vessel was thin-walled. Usually you can assume it for anything in this course, but in general, you would potentially want to check that the radius versus the thickness is over 10 of a factor. So before I move on, does anyone have any questions associated with this problem, or more generally concepts so far before I start example 2? I'm not going to drink the coffee as much as I want to. I don't want to gulp in your ears. Why does thin wall matter in this problem? Good question, Jack. So what you would need to actually doesn't matter. So yeah, actually it wouldn't really much because we're not really we're only looking at stress in the bolt and not in the pressure vessel itself. So good point. If anything, it would be the radius. So whether it be the spec radius would be to the middle of the wall, but that's sort of minor. Otherwise, yeah, you're right. Actually, we didn't really we didn't really care about thin wall looking at it a little more closely. Good call. Yeah, it's really just for the pressure vessel itself. Anyone else? Are the bolts in tension? You tell me. So, what's the sign on my stress? And would we expect them to be, right? If we have an internal positive pressure, just picturing the bolts for a second, right? Do you expect the bolts to be under compression or under tension? And at this point, anyone can answer this if you'd like. So they are in tension indeed, right? So if you have a positive internal pressure, what it's going to result in is the object trying to be, exactly, it's trying to expand. So if the object's trying to expand, those bolts are going to have to hold it back from expanding. And so what would happen is if you had compression, you need a negative internal pressure, which would in turn cause forces to be like if I were to draw this arrow the other direction and get a positive result, yeah, you'd either need a negative pressure or you would need those forces to show you that they're pointing the other direction to be working against the bolt that way. And in fact, this brings us really nicely to our next question, which is exactly this, where we have a spherical chamber that's made in two halves, where it's going to be a vacuum chamber. So we're going to actually apply a negative internal gauge pressure, which would be, again, the difference of the internal versus the external pressure. And we'll say that instead of there being bolts frequently on vacuum chambers, you just put a lid on it or something, and the negative pressure will just pull it down to the surface. In fact, the one I use for lab, it has a rubber gasket, which rubber versus or rubber in contact with metal has quite a high coefficient of friction. So let's say we have a coefficient of friction we know to be mu equals 0.5, and we want to find what the normal force to separate the two halves would be if we were to just try and pop the two pieces apart like a Kinder egg. Or we had a shear force to try and slide one half with respect to the other versus the torque that we need to actually apply to twist the two pieces apart. And so this would tell us, how would we open this, possibly inform design as to how the two pieces would fit together. All right, so if we start here and then let's try and draw an FBD of what exactly we're looking at going on this half of the object. So the first part is the pressure that we're applying, right? So we're going to again have this pressure being applied where we've cut through the what would ordinarily be the gas, but now it's a very low pressure gas. Can't quite get all the gas out, but we have a low pressure gas. And if we want, we can draw this operating in tension. We could say that since the pressure is negative, we want it going that way, right? So it's like a normal force, but we're just flipping the arrows to show that it's working the other way. We don't have to. We could leave it as negative if we wanted. And then the other things we care about with this particular cut, let's say this is a cut through the theta direction. So we're going to have all of these additional, whoops, drawing these the wrong way. We're going to have these additional compressive stresses from the contact of these surfaces. So a whole lot of sigma theta thetas here being the cut through that plane, the area being pointed in that direction, and just force being carried between those that we're distributing over that area, which we'll call A theta. And then locally, we're also going to have a whole bunch of, if we try and twist this thing, we'll have a whole bunch of shear. And so we have to care about the shear as well, shear stress. And this will be varying in direction, but all operating on this area here. So these little arrows are going to represent our shear stress, which we'll call, actually I'll label it up here. This will be tau theta phi, because it's going around in that phi direction as well. So to get the compressive stresses in the walls, we need to find our sigma theta theta. And so this, since we don't have any additional external pressure, we're just speccing the gauge pressure here, we can use this approximation of P times R over 2T. And then this will be equal to that negative pressure that we have in there. We could have taken that into account and done the full balance equation if we wanted, and we would have flipped PR over 2T, but we could just put in the negative pressure directly if we want to the formula. We have times 0.5 meters, which is the radius here, divided by 2 times the thickness, which is 10 millimeters. And this will give us a value of minus 2.5 MPa. All right, and then if we have the force to separate these two, we just take the force divided by that area, right? And so the amount of force that we take would be that stress that we've just determined is being applied to the walls. We have to overcome that stress, and we know what the area that force is being applied on is. So we have sigma theta theta multiplied by A theta. So we can have an expression for what A theta is. And so we have that thin disk again, which when we subtracted R minus T over 2 squared from R plus T over 2 squared, we just got an expression of 2 pi big R times T. And so we can plug that in right here for A theta, 2 pi R times T, and get a number on that by plugging in our values here. Minus 2.5 MPa times pi times R is 0.5 meters, multiplied by T is 10 millimeters. And so we'll get our value for our force, which is 78.5 kilonewtons. So this would be the amount of force it would take to pop the two halves apart. And finally, if we want to check in shear, there's a relation between shear in friction and the normal force, right? So what is, how do we get that relation? What do we need to incorporate now? I'll open that up to the chat if that wasn't clear. Yeah, we need our friction. Exactly, we need our friction. So because our normal force and our shear force are related by the coefficient of friction, and we want to make sure these are beginning to move, the maximum force that this system can experience before that starts moving is a shear force equal to mu times the normal force, which in this case is just mu times F, which is our normal force, which is just 0.5 times 78.5 kilonewtons, which gives us a shear of 39.27, well, 39.3, let's say, kilonewtons. So I want to note something first. Which way is easier to open this vacuum chamber? Right? Agreed. So it seems like shear is the easier way to open this, and that's because our total amount of force we need to apply is lower, right? It takes only half as much in shear to pop the two pieces apart versus actually pulling them apart, which is twice as twice as energy inefficient, I guess. So exactly, that's something we would have to care about in a design situation. So if we then want to find the actual torque it would take to spin the halves, we can we can go towards our shear stress and see if that's also going to be limiting. And if we then know what our shear force uh, would be, or if we needed a lower shear force in order to do this, we could try that too. So we could take our shear stress now as the it's again going to be pointed in that direction, but it's going to be specifically for twists. So we'll take V over A theta. We'll still have this same relation of friction here. And since we know that F over A theta is sigma theta theta, this tells us something about the relation between our shear stress and our normal angular stress as well, or normal hoop stress as well. So this is useful. This then gives us a value for what our shear stress would be if we were to try and rotate this thing. And so we can turn this into a torque using the torque equation. So if we have our uh, tau being TR over J, we can then get a value for what the torque has to be from the shear stress, which is tau um, theta phi times J divided by R. And we specifically want the max of this because that's going to be at the outside, right? We know what J is for a thin-walled cylinder, which is 2 pi r cubed T from that lecture where we covered the polar moments of area. And so we can just get what our torque is here, which is 1.25 MPa multiplied by 2 pi times 0.5 cubed times 10 millimeters. And that's not just 0.5 cubed, but 0.5 meters cubed. And so we get a final amount of torque it would take as 19.6 kilonewtons times meters. So this is how we can get towards, our design criteria of, well, if you need to open this and you want to create an object that's going to help open this, if you give it a longer moment arm, it'll take a little less force, and so you'd be able to do that, or something like that. So that's sort of how we can use some of these. And at this point, it's radius b squared, probably. Yes, good call, Aditya. Thank you. Indeed. Yeah, there's an r cubed over r. Good call. And so, yeah, this gives us our design criteria if we were to build something like this, right? So finally, I have one more example. If I'll work through it for posterity, and so you guys have the example worked out. But like I said, feel free to go if you'd like. No pressure, so to speak, to stay if you really can't. So let's say we have an object that's under pressure, but under a varying amount of pressure, like in the dam question in the problem set, like in that dam question in the problem set. So if we have a fluid in a container or grain in a silo, something like that, that's where we would have a varying pressure as a function of position vertically. And so we want to be able to handle those two and determine, where would we have to be concerned about a material like this, or a structure like this failing. So we can go at that by a pretty similar method to what we've done with height varying density problems, or not height varying density, but height varying force problems due to a uniform density. So if let's say we have a height z over on the left here, this will have a height z, and we want to find out the amount of total force this fluid in this canister is going to be applying, the amount of force this fluid is going to be applying due to just having a distributed load. How much is that in total? How do we get that the total force here? Yeah, so we're looking to find first off, we have a centroid, and exactly, we have some density we need to assume. So yeah, agreed. So we have a cylindrical thing, so we have an area, we have a pi r squared, we have a height that we care about, z, and then the total force due to gravity, which is another rho times g. Agreed. So that's the total amount of force this is going to be applying downwards in this specific cut version of the silo, where we might have a whole bunch of fluid below this, but we're looking at what the total force being supplied by, for example, these walls. These walls is going to be, right? It might be something we care about. All right. So if we then try and do, first off, we have our pressure that then is going to be dependent on our amount of fluid above us, which is just rho times g times z. But we can do this force balance now and determine what our forces are. But it turns out if the pressure is going to be rho times g times z, and we go to balance the vertical pi r squared z times rho g, it turns out the pressure absolutely balances the fluid above it, and so no axial stress is being carried by the walls, which makes sense actually, because unless the walls have their own weight to them, they're not really supporting any weight. So our nz here is actually just zero. And again, it's because if we had friction, it'd be one thing where there was like grain pulling on the sides of the container, but there's not for fluids. So our axial force being carried by the walls is zero. But if we look at our hoop stress, we're going to get a different story here, right? So we can plug in what our pressure value is here and get this rho times g times z times big R divided by T, and that's all it is. So this is our axial stress, sorry, not our axial stress, this is our hoop stress for grain in a silo or water in a container or something like that. So at this point, I'll take any questions if anyone has any, but we can also move discussion to office hours at this point. So I'll wait a little for questions now. So if not, I'm going to express just a final note of appreciation. Thank you guys for being here. I know it's a weird schedule and lectures are slightly longer, so I can go through all the problems, but Thank you for being here. What is this expression for again? Good point, Andrew. I definitely should have. Or is it going to be Ice Ice Baby? That's the worst kind of Russian roulette there is. There's a game we played in college, and it was the worst. So yeah. So what is this expression for? So Victoria, it's the pi r squared z rho g is the total amount of force being applied by the weight of the water or whatever fluid there is inside the silo. So if you take where the centroid is, apply gravity to it that's uniform, take the total volume of that, that's what you get. All right. Well, on that note, as I should probably really just pull up Under Pressure by Queen. Next time, actually, I need to figure out how to stream music in directly, so it's not just playing in my ear. Also, so I can have like nice elevator music before a lecture starts. No, I appreciate you all being here very much. So thank you. See you all potentially at office hours, and I think most of you should have gotten this note that the homework is due Monday. If you're not getting announcements from me on Canvas, make sure you are, and do check the page regularly. But no, we're continuing with lecture normally. I just skipped the Wednesday class date, and I'm going to catch up on Monday where we do both combined loading theory and also examples. All right. Okay. Well, that's me signing off. Thank you for being here, and I'll see you all in office hours.